In this video, we'll learn how SVM, which is short for Support Vector Machine, does classification differently compared to other algorithms, like logistic regression, which simply draws a line between two categories. We'll learn how it chooses the safest boundary by maximizing the margin, why only a few points, which are the support vectors, actually matter, and how SVM handles code boundaries using the kernel trick. And at the end, I'll show you the two knobs, C and gamma, that decide whether your model becomes dangerously picky or confidently general. Welcome to Schovia, where we make AI concepts feel like everyday ideas. In the last video, we used logistic regression to draw the line between two categories like tumor and not a tumor. But here's the problem. There isn't just one line that separates the data. There are infinite lines. Look at these three lines. They all separate the red dots from the blue dots perfectly. Mathematically, they are all correct. But if you had to bet your life on one of them to predict a future data point, which one would you pick? You'd probably pick the one in the middle, the one that keeps the safest distance from both groups. The SVM algorithm doesn't just find a boundary, it finds the perfect boundary. Think of SVM not as a line but a street, where the goal of SVM is to make the street as wide as possible. In machine learning terms, we call the width of the street the margin. The wider the margin, the safer our predictions are. If we draw a line that's too close to the red dots, a slightly unusual red dot may cross the line and get misclassified. The center line of this street is our decision boundary. The goal of the math is simple: maximize the width of the street. Now look at these specific data points touching the edge of the street. These are the VIPs of this algorithm. We call them support vectors. Why support? Because they're literally supporting or holding up the street. And here's the mind-blowing part. You could delete all the other points in the data set, the ones that are far away from the boundary, and the line wouldn't move an inch. SVM cares only about the most difficult points, the ones right on the edge. It ignores the easy stuff. This makes it very different from the other algorithms that try to average everything out. Now, if the data is mixed together and impossible to separate perfectly, we just relax the rules. We treat those overlapping points as acceptable errors rather than ruining the model trying to fix them. But life isn't always a straight line. What if your data looks like this? A cluster of red points in the middle surrounded by blue. No matter how you draw a straight line here, you will fail. You need a circle. But SVMs are linear classifiers. They love straight lines. So are we stuck? No, we use something called the kernel trick. Imagine these dots are on a sheet of paper. You can't separate them with a single tear. But what if we lift the data into a third dimension? If we lift the red dots up, suddenly we can slide a flat sheet right between them. When we look at the flat sheet from above, which is kind of like 2D, it looks like a circle. But the kernel trick allows us to project complex data into higher dimensions where we can easily separate it with a straight slice. When you use SVM in code, you'll see a parameter called C. Think of C as how strict the teacher is. A high C tells the model you must not make a single mistake. The model will create a narrow road to satisfy that. This is often overfitting. A low C tells the model it's okay to miss a few points if it means we get a wider, simpler road. Usually, we prefer a wider road with a few mistakes over a perfect road that's too narrow to be useful. So, while logistic regression gives you a probability, SVM gives you the safest possible margin. It is fantastic for smaller, complex datasets where precision matters. But SVMs can be slow on massive datasets. If you have millions of rows of data, or if you want to understand why a decision was made using a flowchart style, you need to check out our video on random forests. Thanks for joining us on Schovia Labs. Hit that subscribe button for more eye-opening insights, and as always, stay curious.